We'll start in 1 minute. In a few minutes, we'll start section 11.4 on the comparison tests. But first, we'll look at some more examples from section 3. We'll determine if the infinite series converge or diverge. This one, 1 plus 1 over 8 plus 1 over 27 plus 1 over 64 and so on. If we write this in sigma notation and start at n equals 1 and go to infinity, well, it looks like the terms are 1 over n to the third. And you can verify that, that's the right infinite series. This is a p series. Value of p is equal to 3. So that means this infinite series converges. Okay, the next one, 1/5 plus 1/7 plus 1/9 plus 1/11 and so on. In sigma notation, starting at n equals 1 and going to infinity, well, the numerator is 1. So how do we determine what the denominator is? Notice that the denominators increase by 2 at each step. So that means we're going to need a 2n. Well, when n is 1, 2 times 1 is 2. So if I add 3 to it, I'll write 2n plus 3 in the denominator. And then it's not a bad idea to go ahead and check that 1 over 2n plus 3 is the correct term. Let's just do a couple of them. When n is 1, 2 times 1 plus 3 is the denominator 5. When n is 2, 2 times 2 plus 3 is 7, and so on. So this works. And how do we determine if this converges or diverges? Well, if we assign f of x to be the function 1 over 2x plus 3, this function is positive for x values greater than or equal to 1. It's continuous, and it's decreasing. One way to verify that it's decreasing is to show that the derivative is negative for x greater than or equal to 1. So if you compute the derivative using the product, or the quotient rule, I mean, the derivative of 1 is 0, so 0 times 2x plus 3, and then minus the numerator times the derivative of the denominator, which is 2, all over 2x plus 3 squared. So I might as well simplify the numerator a little bit. We have -2 in the numerator, and the denominator is 2x plus 3 squared. And this derivative is clearly negative for all values of x greater than or equal to 1. So that means the function f of x is decreasing. That means we can use the integral test to determine if this series converges or diverges. So with the integral test, we compute the improper integral from 1 to infinity of 1 over 2x plus 3 dx. So we write this as the limit as b approaches infinity of the integral from 1 to b of 1 over 2x plus 3 dx. Well, if we multiply the integrand by 1 in the form 1/2 times 2, I should have done that in the previous step, but so multiply the integral by 1/2 times 2, put the 2 over 2x plus 3 for the integrand, and then compute that integral. We get the natural log of 2x plus 3 evaluated from 1 to b. So I'll leave the rest of this for you to do. I'll just mention that the natural log of 2b plus 3 as b goes to infinity is infinite. So this limit goes to infinity. So that means the series diverges. So this is equal to in infinity, the series diverges. Okay, the next one, the series, the terms are 2 times the natural log of n over n as n goes from 1 to infinity. Does this converge or diverge? Well, assign f of x to be 2 times the natural log of x divided by x. For x greater than or equal to 1, f of x is greater than or equal to 0. So it's only 0 when x is 1, and after that it's positive, and it's continuous. In order to use the integral test, we would have to verify that this function is decreasing. So if we can show that the derivative is negative for x greater than 1, then we'll know that this function is decreasing. So the first derivative, the derivative of the numerator is 2 times 1 over x. We multiply that by the denominator x. And then we subtract the numerator, 2 times the natural log of x times the derivative of the denominator, which is 1, and divide by the denominator squared. Okay, so 2 times 1 over x times x is just 2. 2 minus the natural log of x, all over x squared. And this is less than 0. So I'm missing a factor, aren't I? So 2 minus 2 times the natural log of x. So the numerator is 0. When the natural log of x equals 1, or when x equals e. So the first derivative is always negative for x greater than e. Okay, so as long as the function is eventually decreasing, we can use the integral test. Okay, so the improper integral of f of x from 1 to infinity, 2 times the natural log of x over x dx. Yeah, this one we can use u substitution. If u is the natural log of x, then du is 1 over x dx. So we see the natural log of x, and we also see 1 over x dx. And then the constant 2 can be brought out front. And so the integrand is just u du. And then the lower limit, when x is 1, the u value is the natural log of 1, which is 0. And when x goes to infinity, u also goes to infinity. So we can see that this is going to be, it will have an infinite value. So as u goes to infinity, this is unbounded, so this equals infinity. That means the series diverges. Okay, the next example, the series n times e to the negative n. So let's pick f of x to be either x times e to the negative x or x over e to the x. Either way is okay. I'll just write it as x times e to the negative x. For x greater than or equal to 1, f of x is positive, and it's continuous. But is it decreasing? So let's compute the derivative, f prime of x, using the product rule. So the derivative of x with respect to x is 1. So 1 times e to the negative x plus x times the derivative of e to the negative x, which is negative e to the negative x. And we can factor e to the negative x out. And we have 1 plus x times negative 1, or just 1 minus x. And this is negative. E to the negative x is always positive, and 1 minus x is less than 0 when x is greater than 1. So we can use the integral test because this function is decreasing for x greater than 1. So the integral from 1 to infinity of x times e to the negative x dx. Okay, so let's use integration by parts. U is equal to x, so du is dx. dv is e to the negative x dx. And so v is negative e to the negative x. Okay, then we have negative x times e to the negative x. Evaluate this from 1 to infinity. And then we're subtracting the integral from 1 to infinity of v du, which is negative e to the negative x dx. Okay, so let's just write the limit as b goes to infinity of negative x times e to the negative x from 1 to b. And we'll do a couple of things at once. We're subtracting a negative, which means we're adding the integral of e to the negative x. But the integral of e to the negative x is negative e to the x, negative e to the negative x. So we can write this as minus the limit as b approaches infinity of e to the negative x from 1 to b. Okay, so when we evaluate this, we get, let's write it as negative b over e to the b instead of e to the negative b. And then we're subtracting a negative, so we're going to add 1 times e to the negative 1, or just 1 over e. And then the other one, we're subtracting uh, 1 over e to the b minus 1 over e. This is also as b goes to infinity. So here we have, when we allow b to go to infinity, we have infinity over infinity. So using L'Hopital's rule, this will become negative 1 over e to the b, right? So this term will go to 0. This term will go to 0. So it looks like the surviving terms are 1 over e, and then minus negative, minus is plus 1 over e. So we get a finite number, 2 over e. So since the improper integral converges, we conclude that the series also converges. Okay, let's move on to the next section, 11.4. This is the section on comparison tests for determining whether series are convergent or divergent. So make sure you note the setting for the comparison test. We have two series, the series of the a sub n terms and the series of the b sub n terms that are all positive. So all of the a values are positive and all of the b values are positive. So the comparison test says if the b sub n series is convergent and a sub n is less than or equal to b sub n for all n, then the series of the a sub n terms is also convergent. So we'll do a sketch of proof. It seems like the result of part one is as it should be, but we'll do a sketch of the proof. So we'll define S sub n to be the sequence of partial sums from the series of the a sub n terms. So S sub n is the sum of a sub 1 plus a sub 2 and so on up through a sub n, and we'll assign T sub n to be the sequence of partial sums for the b sub n series. So T sub n is the sum of the first n terms, b sub 1 plus b sub 2, and so on up through plus b sub n. So we're doing a sketch of proof for the first part. Since a sub n is less than or equal to b sub n for all n, it follows that S sub n is less than or equal to T sub n for all n. And we're given that the series of the b sub n terms is convergent. So that means that the limit as n approaches infinity of T sub n, where T sub n is the sequence of partial sums for the b sub n series, this is equal to the infinite series of the b sub n terms, which is equal to a finite number t. Okay, so what does this mean? This means that the sequence S sub n is an increasing sequence that is bounded above. We know that S sub n is increasing because all of the terms from the a sub n series are positive. So S sub n is increasing as n increases. And we also know that S sub n is less than or equal to t for all n, all natural numbers n, or all positive integers n. So you might remember the monotonic convergence theorem from a couple of weeks ago. So the monotonic convergence theorem from section 11.1. This theorem says that if a sequence is increasing and it's bounded above, then it converges. So by the monotonic convergence theorem, the limit of S sub n as n approaches infinity, which is equal to the series of the a sub n terms, is equal to some finite number s, we'll say. Okay, sketch of proof for 2. This time, if the series of the b sub n terms is divergent and a sub n is greater than or equal to b sub n for all n, then the series of the a sub n terms is also divergent. So it seems to make sense that it should work that way. Okay, so we'll use S sub n the way we did in the first part, and T sub n also from the first part. But this time, A sub n is greater than or equal to B sub n. So for part 2, that means S sub n is greater than or equal to T sub n. And since the B sub n series is divergent, the limit as n approaches infinity of T sub n is equal to infinity. But since S sub n is greater than or equal to T sub n for all n, well, it's reasonable to conclude that the limit of the series S sub n is also equal to infinity. But this means that the series of the a sub n terms diverges. Okay, let's look at our first example. Does the series of the terms are 3 over 4n minus 3 as n goes from 1 to infinity? What do you think? Does that series converge or diverge? So a rare chance to contribute. So go ahead and type in. What do you think? Does it converge or diverge? Well, we'll use a comparison. We'll use the comparison test. Okay, we have 2 answers online, and they are different. So at most 1 is correct. Well, exactly 1 will be correct. Okay, we're going to compare this series with another one. Okay, so I'm going to construct the series. So note that 4n is greater than 4n minus 3 for values of n greater than or equal to 1. So we're all in agreement. 4n is greater than 4n minus 3. And then a fact about arithmetic. If 4n is greater than 4n minus 3, then the reciprocal of 4n, which is 1 over 4n, is less than the reciprocal of 4n minus 3. So 1 over 4n is less than 1 over 4n minus 3. If we multiply both sides of this inequality by 3, this inequality is preserved because we're just multiplying both sides by the same positive number. So 3 over 4n is less than 3 over 4n minus 3. Okay, if I use the series from n equals 1 to infinity of 3 over 4n, and then factor 3/4 out of every term and write it as 3/4 times the infinite series from n equals 1 to infinity of 1 over n. This series is the harmonic series, which we showed diverges. And so 3/4 times that series still diverges. So this is divergent, or we'll just say that it diverges. And so by comparison, since 3 over 4n minus 3 is greater than 3 over 4n, using the comparison theorem, the given series that we started with this also diverges. When using the comparison theorem, well, after you get some practice, you'll get an idea of whether or not the series should converge or diverge. And that will help you to pick an appropriate series that you either that you know diverges or converges. Okay, let's try the next one. Does the series of the terms 1 over n factorial as n ranges from 1 to infinity, does that converge or diverge? So just a reminder, n factorial means the product of the first n positive integers. So n factorial is n times n minus 1 times n minus 2, and so on. At the other end, we have 2 times 1. You don't really need the 1, but I think it's probably included in the definition. So do you think this should converge or diverge? Well, n factorial gets big pretty fast. So 1 over n factorial gets small pretty fast. So can you think of a suitable series to compare this one with? There's more than one option, but you don't need to get too fancy. So remember the P series? So we'll just remind ourselves, if we have a P series, 1 over n to the P, the P series converge for which values of P? P greater than 1, and they diverge for values of P less than or equal to 1. Okay, so the larger the P value, the smaller the terms 1 over n to the p are. Because if p is greater than 1, then the denominator is big, but 1 over a big denominator is small. So since n factorial gets really big really fast, and that means that 1 over n factorial gets small really fast. So my suspicion is that this converges. So for the comparison test, I'm going to pick this series of 1 over n to the second. So we can verify that n factorial is greater than or equal to n to the second for values of n that are greater than or equal to 4. I should just say n factorial is greater than n to the second instead of greater than or equal. When n is 1, they are equal. 1 factorial equals 1 squared. 2 factorial is just 2. That's smaller than 2 squared. 3 factorial is 3 times 2, which is 6, which is smaller than 3 to the second. And then 4 factorial, 4 times 3 times 2 is 24. 4 squared is 16. So n factorial is strictly greater than n squared for n greater than or equal to 4. So what does that mean? That means 1 over n factorial is less than 1 over n to the second for n greater than or equal to 4. And so by comparison, the infinite series, if we start at n equals 4 and go to infinity of 1 over n factorial, that has to be less than the p series starting at n equals 4 of 1 over n squared. So we're just missing a finite number of terms from this one. So if we just add those 3 terms, it's still a finite number. So this is less than infinity. So we conclude that the full series from n equals 1 to infinity of 1 over n factorial converges. Okay, let's move on to the next page. And here's another comparison test called the limit comparison test. Suppose that the series of a sub n terms and the series of b sub n terms have positive terms. If the limit of a sub n over b sub n as n approaches infinity is equal to c, where c is a positive finite number, then either both series converge or both diverge. Okay, so let's let, in our sketch of proof, let's let m, lowercase m and capital M be positive numbers, such that lowercase m is less than c, which is less than capital N. Since the limit of a sub n over b sub n as n approaches infinity is equal to c, I'll go ahead and write it. Since the limit as n approaches infinity of a sub n over b sub n equals c, that means the a sub n over b sub n terms can be made arbitrarily close to c, as close as you want. So there exists a natural number capital N such that lowercase n greater than or equal to capital N means that m is less than a sub n over b sub n, which is less than capital N. So that makes sense. If we multiply all three parts by b sub n, then we have m times b sub n is less than a sub n, which is less than capital M times b sub n. So we have two cases to consider. Let's suppose the series of the b sub n terms converges. Then the series of the m times b sub n terms also converges. Because all we're doing is multiplying each of the terms from the convergent series by the same positive number. And since a sub n is less than m times b sub n for all n, it follows that the series of the a sub n terms converges. Because a sub n is less than m times b sub n for all n. So in this proof of the limit comparison test, we use the first comparison test to reach that conclusion. And then similar type of argument in case 2, this time we suppose the b sub n series diverges. Well, if the b sub n series diverges, then the series of the lowercase m times b sub n terms also diverges. But since lowercase m times b sub n is less than a sub n for all n, this time it follows that the series of the a sub n terms diverge. So the series of the a sub n terms diverge also, or diverges. Okay, it seems to make sense. Let's look at a couple of examples where we use the limit comparison test. So in the next example, does the series, the terms are 2 over 3 to the n minus 7. So that's an exponent n. So 3 to the n minus 7 is in the denominator. So what do you think should happen? Should it converge or diverge? The numerator is just a constant. And the denominator, 3 to the n minus 7, the denominator is going to get big pretty fast. So my suspicion that it's going to converge. But do you have an idea on what series to use in the limit comparison? So there's a geometric series, 1 over 3 to the n. This geometric series converges. So this one can be written this way. It's 1/3 times 1/3 to the n minus 1. So the common ratio 1/3 is between -1 and 1, so this converges. So if we compute the limit as n approaches infinity, so in the numerator I'll put 2 over 3 to the n minus 7, and in the denominator 1 over 3 to the n. Then we'll simplify the complex fraction. Dividing by 1 over 3 to the n is equivalent to multiplying by 3 to the n. So 2 over 3 to the n minus 7 times 3 to the n over 1. So we get 2 times 3 to the n over 3 to the n minus 7. Okay, in the denominator, as well as the numerator, well, we see a 3 to the n. So if we multiply by 1 in the form 1 over 3 to the n over 1 over 3 to the n, this might make it a little easier to see what the limit is. Okay, so in the numerator, 2 times 3 to the n times 1 over 3 to the n is just 2. And then in the denominator, 3 to the n minus 7 times 1 over 3 to the n is 1 minus 7 over 3 to the n. And then as n goes to infinity, 7 over 3 to the n goes to 0 because the numerator, or the denominator, goes to infinity. So this limit is 2 over 1 minus 0, or 2. Okay, so since our Since the series that we picked for comparison converges, since this is a geometric series that converges, the limit comparison test means that the given series also converges. Okay, so we have less than a minute left. So I'll use up the time until it's over. What series would you use to compare this series with? No, we're out of time. So tomorrow we'll look at this example and the rest of section 11.4. So go ahead and sign in for attendance.